Yeah, of course. Yep. All right, so let's start then. So we were discussing, right? So our goal, right, is to understand the integral, right, of some adapted process against Brownian motion. So adapted, right, means that whatever you're trying to integrate against the Brownian motion must belong to the Brownian motion filtration. You know, roughly speaking, all it means is this. If we observe, right, W on the time interval 0 to S, then we should know yes. All right. Basically, what this means is you cannot pick ahead. All right. So you think of it like this. Basically, remember that sort of like one of the motivating example we have is something like this. Right, where this is the number of shares, right? And of course, this is a stock. And so remember, the stock is essentially driven by the Brownian motion. So the stock, right, is an adaptive process, meaning that if you observe the Brownian motion up to time t, then you should know the stock, right? And well, you can also see this through your simulation, right, of the homework. Basically, you use the Brownian motion values to simulate a stock value. And you see that, right, if you number of shares, right, should also satisfy the same properties. Because if this is not true, what you can do is you can use future information to formulate your portfolio, and you can realize, you know, some kind of gain in a weird way. All right. So these are just technical conditions right now. It should be pretty natural, right? You've been doing it so far. I just want to kind of highlight it like this, right? When you do simulation, just notice that these are automatically satisfied, right? You don't do anything more weird than that. Okay, and so our goal is to just understand basically this stochastic integral. And we pointed out, right, that the difficulty exactly comes from the fact that the Brownian motion, right, is nowhere differentiable. Okay, because essentially, if you want to understand, right, suppose we don't have W, we have something else. Suppose we have like a function f, right, is differentiable. Then if you want to, right, integrate, let's say, another function against the change of f, then what you can do is you can just sort of do the divide and multiply by the change in time trick. And what you have right here, right, is exactly the derivative, which we assume to exist. Right. And so this is just your good old Riemann integration. So in other words, right, what we understand so far, right, for some integral like this comes from, right, basically our knowledge of the Riemann integration, or basically we want to relate, right, the change of the function with the change of time itself through the derivative. Okay. Now, of course, right, because Brownian motion is nowhere differentiable, this technique is not available to us, right? This technique is not available to us. And I was also trying to kind of show you how intuitively you can see that the Brownian motion is nowhere differentiable. So I guess evidence, right? That WT is nowhere differentiable. And for that, we introduced the idea, right? The concept of the total variation of some function, some process, right, on the time interval, which basically will be the sum, right, of the absolute value of the changes, but then you take the limit, right, as time interval goes to 0. And we remark, right, that if f is differentiable, if you have a differentiable function, then the total variation on a time interval will be just the integral, right, of the absolute value of the derivative, which is finite, right? And so we say, right, that this is the piece that you can check. That's the evidence, right? You can check by Monte Carlo simulation, right? You can simulate a Brownian motion path, and you can push your time to go to 0, and you can observe that this quantity, right, is going to get larger and larger as you push time to go to 0. Okay, so that's something that you can check, and I'll ask you to do that during this week's homework. But anyway, right, so it's just a fact for now, right, that the total variation. And you'll see, we'll also try to explain this mathematically a little bit. Right. Now, let me, okay. So intuitively, right, why is the fact that total variation equal to infinite kind of points to the evidence, right, that Brownian motion is nowhere differentiable? Well, you can see it in several ways. The first is that, right, if something is differentiable, then its variation must be finite, right? So contrapositively, right, if this is not true, then this is not true, right, in some way. Sorry, this is not true, right? Now, another clue is this, right? Notice that here I'm just defining it from 0 to t for convenience, right? The definition doesn't really have anything to do with 0 to t. You can do it on any time interval, right, from s to t, for example. Also, you can see, right, if the Brownian motion variation is from 0 to t is infinite, then there's no reason why, right, the total variation on any other time interval is finite. Or if you will, right, what I'm trying to say is, yeah, it's fine, right? Here, this is like this for any ST. And the key for you to take a look at is here, right? Try to think that, because it's true for any ST, or, you know, equivalently here, you can just think of this is true for any small t, right? What that means is no matter how close S and T is, right? Doesn't matter how small t is, right? Or how close S to T is, this will be infinite. So that's strange. Now, again, to drive this point home, I guess total variation is a word, right, in math. What's the corresponding concept in physics for total variation? In physics, what would they call total variation? If you think of the function as position, then what's total variation?
Is it like total distance that you travel?
Exactly, that's total distance travel. And there, right, you see something remarkable, right? And of course, right, that's right here, right? Total distance travel is just speed, right, which is absolute value of velocity, right, times time and add. And here, right, what we're saying is, doesn't matter how small a time interval is, the ground motion will travel a total distance of infinite. All right. And that, if that's not mind-blowing, then I don't know what is, right? Because again, right, try to think about it. Doesn't matter how close S and T is within this time interval. Remember, ground motion is like random walk, right? It's the infinite version of random walk. It's the continuous version of random walk. Doesn't matter how close the two time points is, the ground motion has traveled an infinite distance. Okay. So that's why actually ground motion, even though it's a very routine object we use, is pretty mysterious in certain ways. All right. I mean, if you try to think of certain kind of properties, that's why like that the whole class can be devoted, right, to studying ground motion. Anyway, right, strange things like this certainly point to some very strange behavior in the past. All right. So that's just why I want to point out. Any question? So now, let's continue on this concept, but take it one level further. What we are really after is something called quadratic variation. Okay. So I guess I use TV, right, up there. So I use QV. Actually, the right notation is actually this: the quadratic variation of a process. All right. And let's do this. Okay. Will be the sum, but now you square the change. And then you take the limit as delta t goes to 0. Okay. So there's just one thing here I want to kind of write. So basically here, right, it's the same thing as the total variation. Except that, right, instead of having this as absolute value, now you square. Okay. One more thing is this, that, you know, by default, in this kind of context, we start the process at time 0, right? We start the process at time 0. So technically speaking, we just can denote this by WT, right? And that's understood as this. The reason is, if this is the case, then we have a function, right? A function of time. Yes, this is a function of time, which measures the quadratic variation of the whatever you want, right? Here, ground motion, but can be whatever, right? This concept is general from time 0 to time t, right? So the only thing is we understood conventionally that we start at time 0. It's kind of useful, right, for this reason. That so several remarks, right? First of all, you see that the quadratic variation, how does the quadratic variation behaves as t increases?
It should increase, I think.
Right, because basically you just have, it's very easy, right? Look at, you just block it from 0 to s, and you have from s to t, right? And basically you just do a division from 0 to s, and you do division from s to t. So therefore, right, is because you square it, it can only increase. Actually, right, I just give a description of the following, right? If I subtract this function, what do I get? I get the variation, the quadratic variation on s to t. Is that clear? Right? Because you block from here to here, you block from here to here, right? It's the same as you block from here to here. Okay? So that's why, right? This notation is useful. Now, why do we bring this up, right? Why do we bring this up? So let's think about this. Quadratic variation versus total variation. Right? Is there any comparison between these two? Is there something smaller, something larger, or there's no comparison? What do you think? The reason is? Well, for all we know, this can be also infinity, right? And also, let's say for the finite one, right? The total variation, the quadratic variation can also be finite and can be bigger, right? So how do you know? Just because it's infinity for total variation for blind motion, right? It could be that this guy's also infinity. We don't know yet, right? So here's the clue, right? Let me ask you. Okay, that's good. Right? These two things, which one is there any comparison between these two? The answer is yes, right? Because here, remember, the context is we're pushing delta t to go to 0. So therefore, this is going to 0 too, right? Because bar motion is continuous. And if it's going to 0, for sure, this is less than 1. Now, if you take a number less than 1 and you square it, what happens? That's right. Okay, and that's the reason why this is smaller. Okay, because you are squaring numbers that are smaller than 1 because you're taking delta t to go 0. Is that okay? So quadratic variation, right? So as Fatima kind of felt, right? is smaller, so it will have a chance, right, where the total variation is infinite. Maybe this one has a chance to be finite, right? So in fact, it turns out that this is the right object to measure the variation of the blind motion. Okay, it's too wild. It's too wild at the absolute value level. It's too wild. It's infinite. But if we square it, then we can tame it, meaning we can measure it, right? It can be finite. So you'll see, right? If a function is differentiable, what do you think the quadratic variation of a function is if it's differentiable? If a function is differentiable, right? No. I'm asking in terms of that. Yeah, it should be differentiable, but even better, right? So if a function is differentiable, the total variation, right, is infinite. So what do you think happens to quadratic variation? Right, the quadratic variation is even better than differentiable. It's just 0. Okay. Now for blind motion, of course, blind motion is not differentiable. I'm not sure. Care to guess what the quadratic variation of W is, of blind motion is? No, right? Because if it's 0, I don't know. It's not. It's not that good. It's T. All right. And that actually, again, gives you a clue, right, exactly on why W is not differentiable. Because, right, that means that the quadratic variation is not 0, so that implies that it's not differentiable. Okay? So this implies W is not differentiable. So we will try to establish these two facts, right? And again, emphasize, right? These are things you can check, right, with your simulation. All right, that's the beauty of having computer access. You can do these things, right? All of this with a computer. I mean, you can check it. Any questions so far? Okay, so let's see why, right? This is true. So let's call this 1, call this 2. Now, why is 1 true? What's the easiest function I can try to find a quadratic variation for? What's the easiest non-trivial function I can find a quadratic variation for? Yeah, the identity function, right? By the way, just so you understand, suppose that I have a constant function. What is a total variation of the total function? Oh, sorry, of a constant function. Zero, right? So even though constant function is probably technically the easiest, it's so trivial, right? Even total variation is 0. There's nothing I can talk about, right? But conceptually, you should try to understand, right, why a constant function has total variation 0, right? I guess it's trivial because your position is always constant, so you are not moving anywhere, right? Anyway, right? So this is the easiest one we can look at for quadratic variation. By the way, right? For this one, let's see, right? For this one, what is the total variation of this function? What's the total variation of this function? Nope. It does move, right? Yep, t. Right? This is something that keeps going up with velocity 1. So of course the total distance traveled is t. All right. But what I'm saying is, right, this is differentiable. And so the quadratic variation is going to be 0. So let's see, right? The quadratic variation of this function is ti plus 1 minus ti squared, right? And take a limit. Right? Now let me try the simplest thing for you. You can prove this generally. So here, right? I guess intuitively you divide like this, right? So how big is ti plus 1 minus ti? How big is ti plus 1 minus ti? Yeah, not only very small, but it's t over n, right? I mean, if we do equal length grid. So we get, right, limit as n going to infinity, if you will. It is, right? It is, but I'm trying it on the simplest function, which is the identity function, right? We'll show this more generally after we show this. But is it okay? Now I'm just showing for the simplest one. And so I think, right, it's clear that this is all right. Okay, so far? So generally, right, if f is differentiable, what can I do with this difference? What can I do with this difference? Well, if a function is differentiable, what can you do? You can use the intermediate value theorem, right? Where this is some point in between the interval. Agree? Thus, calculus gives you that kind of result. Now, what can we do with this? Well, here we say f is differentiable. I guess we kind of say something more. We kind of say it's continuously differentiable, or at least right, the derivative is bounded, right, on this time interval, which is reasonable, right? It's not going to get like super steep. It just, but even if it does, right, the derivative should get bounded on this time interval, which is pretty reasonable assumption. If the derivative is unbounded on that time interval, actually it's going to be very weak. That the derivative, right, is less than a constant, right? Is it okay? So what that means is we can upper bound this by this constant, right? And what's this limit? Zero, right, as we showed above. Okay. So you understand that? So basically, right, you see that the key is because of this calculation, right? So when you have a differentiable function, then you can relate it back to the original calculation. That's what it is. Any questions so far? So I guess, right, the above is kind of so useful that there's even a notation for it. Basically, the above, the notation for it is going to be like this. dt squared is going to be 0, which is establishing or encoding this fact, right, for t. Okay. And so you see, right, this notation is quite useful because if f is differentiable, right, then what is df in terms of et? df is f prime of t dt, right? So I guess df of t, right? So dft square will be f prime of t square dt square. But dt square is 0. So as long as this guy is not infinity, right, which is exactly that thing here, then this is going to be 0. And that's this thing. Again, right, after you establish the proof, then you can use notation, right, to capture that proof. But this will be quicker for our thinking later on. Any question? All right. So that's fact 1, right? What about fact 2? So for 2, right? So what we want is we want this, right? Limit as delta t goes to 0 of WTI plus 1 minus WTI squared, right? Sum. And we want to somehow establish that is t, right? So I'll do something like this first. Let me just take expectation. Right, before I take limit. If I take expectation, right, then I can pass expectation inside. And what is this? What is this? Expectation. Right, right. Remember, this is the change, right, of the Brine motion. This is the increment. By definition, it has normal, right, distribution with mean 0 and variance like this. So therefore, right, this is just the variance. And because, right, we are increasing, so we can do this, right? We don't need to pick up the value. So this is just t. Okay. So what have I shown? What have I shown is that I have shown that the expectation, right, of the limit. So there's something subtle here, but it's okay. I mean, I can pass the limit inside, outside the expectation. So I've shown that on average, right, this limit is t. Right? But notice, right, that's not what this statement is. I'm not trying to say that on average is t. I'm saying individually, right, is each of the path is t. Right? You understand the difference. The difference is here, right? I say if you average out all this quadratic variation, you get t. But no, right? What I really want is each of the quadratic variation for each path is t. Okay? So how can I get there?
Can you show that the variance goes to 0 as t change of t goes to 0?
That's not a bad idea, actually. That's not a bad idea. You could try the variance, even though, right? It's not a bad idea, Kareem. I think that's good. I'm thinking of something a little bit more. I don't know how to say this. A little bit easier, but I think what you suggest also works. What I'm thinking of is a less calculation, but use more concept. So notice, right, what are we doing here? What we're doing here, right, is, so yeah, right. So what Kareem was saying is you can try to also show, right, the variance of this limit, right? You can do this by, again, like taking the variance of each of the term like this and show that somehow, right, it's small. But what I'm trying to say, right, is something like this. So basically, remember, you are pushing the delta t to go to 0, right? So when you sum this, a lot of random variables up independently, right? That's what you're doing here. Right, so basically, limit delta t goes to 0 is the same as limit as n goes to infinity, right, of a bunch of independent random variables, right, what context are we in when we sum a lot of independent random variables that are identical? What context are we in? Oh, I guess, yeah, central limit theorem. I'm thinking of even something easier, law of large number, right? So basically, in terms of law of large number, it should converge to the expectation. Does that make sense? So yeah, I guess I'm cheating here a little bit. There is something about the variance that you probably want to check. But here, right, because when you basically these guys, they're scaled very, they are scaled very well, right? As you divide delta t to be smaller, right, the expectation is always kept constant. So therefore, right, the sum of these random variables, right, they should go to the expectation, which is t. Okay. So yeah, I mean, probably something along the variance like Kareem suggested would be needed, but essentially, yeah, central limit theorem, law of large number will get you that you essentially, right, this limit here is t. You don't need expectation. Are we okay? So in terms of notation, what this is saying is this is dwt square is dt. All right. So these are, so now, right, so this is going to be the quadratic variation. Is key, right, to defining the integral. How come? Right, because after all, right, basically the idea is we want to say that this is the limit as delta t goes to 0 of this sum. Right? But because the prime motion is nowhere differentiable, the change here, right, the variation here is very, very bad. So this limit here is convergent in what sense? Okay. It is not clear you can understand it in terms of the Riemann sum. Because like I said, right, if you want to understand it in terms of the Riemann sum, then you must have differentiability like this. Sorry. If you want to understand it as a Riemann sum, then you must have differentiability like this, right? So because prime motion is not differentiable, it's not clear that you can understand it in terms of a Riemann sum. So what you're trying to do is this, right? You're trying to look at the quadratic variation, or the, how to say this, right? What you can show that basically the sum the notation starts to get a little bit cumbersome here. So this sum, right? Sorry, give me a moment here. sorry, I'm drawing. I'm going kind of like I'm losing what I want to say. So basically, I want to say is this, that when you transition to the quadratic variation, all right, I'll have to gather my thought. It's not super important, but basically we can show. Let me just write like this: that this sequence, right, meaning this sequence in N, converges in the mean square sense. All right. In other words, basically, there is some random variable out there which we denote as the integral, so that when you take the expectation minus this sum, square, it goes to 0. All right, like that. And so maybe let me just leave it like that. So basically, you cannot like define the limit here pathwise. It's not clear, right, because by motion is not differentiable, that this sum will converge point by path by path. But on the other hand, if you square, right, if you take the square on average, then there is then basically this sum, right, this sum right here is Cauchy in that sense. So there is some object that's well defined, and the sum will converge to that object in the mean square sense. All right. Yeah, it gets a little bit too abstract here that I probably don't have an easy way to describe to you. But let me tell you the essential points, right? So, okay. So what I want to say is, right, the conversions here make sense, but only when you pass through the quadratic variation, all right, in the mean square sense. Sorry, I'm not doing a good job here, but this point is really tricky. So let me stop. Let me not go too deep into it. But let me tell you the important points like this. Right? You still see the kind of the effect of the Brownian motion not being differentiable. In this sense, the choice of how we pick the integrand term matters. Okay, so the example I want to use is this integral. Okay. Now, so going through this discussion, all we understand is that this object makes sense, right? We can basically form this sum and it will converge to an object. Okay. So take this interval, T1, T2, right? Tn minus 1, Tn. So now we can form this sum like this, WTI plus 1 minus WTI, right? And take the limit. On the other hand, you might think, right? Well, so basically you're saying, right, on this time interval, let's say, then use WT1, right? Which is right here. That's what I mean by the integrand, right? So this basically means that you use the left-hand point. But if you remember, right, from the Riemann sum, you could do this. Also, right, you could also do this. Let's say the midpoint, right? So this is a right-hand point. Okay. So the point is this, that when you do Riemann sum, all of these choices are reasonable representation of this integral. And when you push delta t to 0, all choices goes to the same limit, right? This would go to the same limit if W is differentiable, which it is not, right? So if we were in the Riemann sum context, Riemann integral, then it doesn't matter what choice you choose for the integrand, they will go to the same limit. So we have one single integral that we mean, by this integral. On the other hand, right, because W is nowhere differentiable, so even though, right, so the discussion above just try to say that when you do this, there is an object that will converge to. But it turns out that this object is highly dependent on what choice you pick here. Okay? Each of the choice here will be different. For the Brownian motion. Is that okay? So that's the point I want to highlight. That yes, in terms of conversions, all of them will converge, no problem. All right, that's the discussion above. Because when you pass to quadratic variation, you can measure the square of the change, right? And it'll converge. But the problem doesn't stop there, right? The problem still continue in the sense that you see the reflection in the choice of which one you use, right? In the integrand. All right. So the one we will go with, as by default, I kind of allude to, is the left-hand point. Okay. We'll use the left-hand point as the one as our default choice for this class, right? So in math finance, or in, I guess, yeah, in math finance, we always use the left-hand point for the integrand, and the left-hand point will reflect into the choice of the Ethos integral. All right. I forgot which one it is. I think this choice right here, I have to check, but the midpoint choice, I think it goes to something called Stratonovich integral. So each of them has a name, and each of them will have their own rule of calculus. All right. So pay attention that when you run, so this has practical implication for you when you run, right, the numerical simulation. Because say if you are not careful, right, and you choose the right-hand point, which happens a lot, then when you push to conversion, you will not get what we get if we use the left-hand point. Does that make sense? So that I'll ask you to do that also on homework, right? So the calculus, right, that we'll study is called Ethos calculus. Are we okay here? All right. So I want to, again, right, kind of try to explain why the left-hand point is a natural choice for us. The left-hand point is a natural choice for us because if you interpret, right, time as moving forward and this as the integrand, then at time ti, right, think of this as like the portfolio choice you want to pick, or as the number of share of the stock you want to hold. Then at time ti, right, the choice you choose can only depend on past information. So it can only be the left-hand point, right? If you pick the right-hand point, that means that somehow you know future information, right? Because you use WTI plus 1. So if you pick even the midpoint or the right-hand point, then that means that you are using future information to pick your stock. And so financially, that doesn't make sense, and it will converge to some integral, some result that doesn't correspond, right, to our financial intuition. Okay, so that's why integral, Ito calculus are the natural choices, right, for us to use in math finance. All right. So now that's a bunch of abstract discussion, but I hope the more you use it, the more it will become natural, right? So our next one is going to be the Ethos Formula. So Ethos Formula is basically, this is like differentiation. Okay, in the presence of ground motion. And so basically the goal is like this. Suppose you have a function, right, of both time and ground motion. And you want to write the differential of this. Your hope is that, right, so basically this is the change, right, of this function of time and ground motion. You want to capture it by something that moves with respect to time and some other thing that moves with respect to ground motion. What are they? Okay. Now, why is this differentiation? It's differentiation because, if you don't have the ground motion, then this is classical calculus, right? So this is classical calculus. Now, what function do we have in mind? Well, the classical function we have in mind is, the prime example we have in mind the stock. Okay. So see, the stock now, right, is a function of T and ground motion. So, right, now we pretend that we have this. Then we want to ask, how does the change in the stock price can be captured with the change in time and the change in ground motion? And the answer is, that's the percentage return that you always know. So that's these two question marks, right? So I guess it goes both ways, right? But the direction we are pursuing is now differentiation, meaning that suppose we have this, we try to differentiate it down to here. Does that make sense? So these are the two question marks here. But of course, right, we want to have a rule that works for any function. Okay. So actually, this is prime example number 1. Prime example number 2 would be something that's already in its perfect form. For example, something like this. Okay. If something is already represented, right, as an integral, what do you think is differential look like in this case? So maybe that's too hard. Let me just drop the bar motion. If I have a function like this, what is df? So remember, right? If I drop bar motion, then you are back in classical calculus, right? What is df here? Correct, right? Because see, it should be f prime of t dt, right? But what's f prime of t? Well, this is fundamental theorem of calculus, right? Which gives you alpha t dt, right? So integrand is good, but don't forget dt, all right? Because we're in the differential like setup, right? So dft, right, is f prime of t dt, which is alpha t times dt, okay? But this is very, very intuitive, right? Because what is this? This is f of t plus dt minus f of t, right? That's a change in f. Well, what is it? That's going to be the integral from 0 to t plus dt, right? Minus the integral. Agree? Well, what is this? This is the integral from t to t plus dt of this. Now, right? So if dt is very small, right? This is t plus dt, right? This is your alpha function. And you're looking at the area of the curve, right? If this is very small, then approximately or exactly, right, in the differential is equal to the change, right? Times the length. So that's exactly what we try to capture. You understand? So if we have two types of integrals, then what should the differential be? Sorry, so I guess I can write f of t, w of t, whatever. But you know what? Let me just write f of t, all right? Because here it's really a process. I don't want to write f of t. It's not really a function of wt exactly. It's a function of a whole path. But anyway, right? What is the differential in this case? Well, again, right? Just think of it intuitively. Right, right? just a small change in f, which, right, by linearity would be something like this. Okay. And when t is very small, then this can be captured by alpha t dt. And this, right, alpha t times the change in the, sorry, sigma t, right? Now this, right, you can see through this kind of picture, right, from the rectangle. This, if you feel a little bit weird about it, think of it like exactly that self-financing condition that we looked at last time, right? If you have a portfolio, right, at time t, you hold sigma t, right? And at time t plus dt, right? And then the change, right? The change in the portfolio value from this time to this time, right? So think of W as the price. Then the change, right? The change, this will capture the change in the portfolio from time t to time t plus dt. Well, what is it? In a small time interval, right? It's going to be just the number of share times the change in price, right? So think of this as share, if you will, and think of W as the price of the stock, if you will. So anyway, right, what I'm trying to say is this integral is captured by this, okay, when we are in a very small time context. Also, right, the reason why we do sigma t like this is because we are always picking the left-hand point for the Ethos integral. So that's the prime example number 2. That if we have a perfect integral, then the differential is just like this. Are we okay so far? All right. So compare and contrast, right, these two examples. The reason why we have to work hard for this one, while the second one is kind of trivial, is because the second one is kind of already set up in the fundamental theorem of calculus sense, right? Everything is set up so that the differential is straightforwardly calculated. Here, right, you might think that this looks compactly nice in terms of formula. Yes, in terms of algebra, yes, this is very nice. But when you try to, right, if you think about it, if you try to do this, it'll become a mess. Why? Because this function is not linear with respect to t and wt. Or not, sorry, not linear in time, right? When you try to subtract this, there's nothing that directly nice that comes out. When you try to subtract the integral, right, because the integral is linear with respect to time, we can always shift the times interval up like that, and we can do approximation. Is that okay? So I want to highlight why case like this, right, or exactly this is something that we need to develop for. Any question? All right. So maybe one more thing, right? And then we'll say what the formula is. Suppose that you could come up with, right, the answer like this. Suppose that somehow we can find this, right, by the formula. What you can do is you can, because, right, basically, if you integrate both sides, right, if they're equal, then you can integrate both sides. The left-hand side is what we say is the integration 101, right? So, sorry. This is S, right? The left-hand side is f of t wt minus f of 0 w0 will be equal to this. So in some case, right, this will get tricky, but this will basically give us an antiderivative when we integrate with branch. Okay. What do we mean by this? Well, very simple, right? I think you guys all know this. What is the answer here? It's not a trick question. What is this? No. No, I'm not asking for this. I'm not asking for D of this. Right? If D of this, then that's TDT. That's correct. I'm asking for this only. Yeah, right. Maybe it's too much abstraction, so you are not following everything. But right, this is just t squared over 2, isn't it? Now, of course, right, you guys took calculus and you're all very good with calculus. So, but then if someone asks you why, how are you going to justify this? Again, right, I mean, I'm not trying to give something that is super deep here, but right, someone asks you why this is true, what would you say? Right. So first of all, this is exactly now what Jingmei was saying, right? If you do this, then you got TDT. On the other hand, if you do this, what do you get? TDT as well. Because right now, this is the derivative. You understand? So, right, you take this abstract formula, right, for granted. And you take the derivative, right? Everything kind of like, is on auto drive mode in your mind, right? But when you encounter something new, then that's when it starts to get a little bit, right, new. But right, I just want to say that what we're doing here is like classical calculus, but with Brownian motion and with some new rules. All right, so we're almost out of time, right? So let me just say something. So this is a difficult lecture, all right? I think this is one of the most difficult lecture we have so far this semester, and maybe the most abstract. So do review this lecture and make sure you understand all the points I said, all right? Because all the points I said are key points, except maybe this one. Well, first of all, I didn't explain it very well. But second, you don't need it so much, right? It just try to tell you that the limit here is well defined, right? And well, frankly speaking, we can accept that by faith, right? In some way. So this part is not super important going forward, But everything else, all right, in this lecture will be very important for you to master calculus, stochastic calculus going forward, all right? So make sure you review this lecture and understand all the points I want to make here, all right? No point here I make is redundant, trust me, besides that one. So now I have a couple minutes left. Let me write down the formula and then we'll correlate, all right? So the Eros formula is like this. The reason is I think that in computational finance with Professor Larson, you guys are using it or about to use it. So we have a function, right, of t and x, right? So x here is standing for by motion. We require it to be C12. What we mean is one time differentiable in t and twice differentiable in x. Okay. So do try to understand, right? It's not weird that x is wt because w, right, is a spatial variable, right? It moves with respect to time, but it itself, right, is just a value, a spatial value. Okay. Then df, right, twt here will be f sub t dt plus f sub x dwt plus 1/2 f of sub xx d of quadratic variation of t. Okay, where, right, all these are partial derivatives. Also, right, as you will see, notation starts to get heavy around here. So when we write this, right, what we mean is you do plug in the argument, all right? It's not like you leave it hanging. But, you know, if you keep writing TWT everywhere, it just gets really super heavy, right? So we drop the argument. So even here, right, we'll drop the argument and say just DFT, all right? Finally, this, right, is just a fancy way to write DT. But you'll see a reason why I want to keep it like this. It is DT, all right? But for the general case, it's good to have this to begin with. So you can compactly write it like this. F sub t plus 1/2 f sub xx dt plus f sub x dwt. All right. So that's Ethos formula for you. Now I know I'm 1 minute behind time, so bear with me here. I'll just want to do one example and we're done. The Black-Scholes formula. Oh, sorry, the Black-Scholes model. Okay, I want to show you that I can apply Ethos formula to this. Now, if you're new to this business, it's good for you to kind of see what the function ftx is. All right, so the function ftx here will be S0 e to the mu minus 1/2 sigma squared t plus sigma times x. Right, where t and x are the variables, everything else are constants in this business. So what's df or ds, right? Well, if you differentiate this function with respect to t, right, that's f sub t, then you get, right, basically this function back times this. So basically you get mu minus 1/2 sigma squared times s, right? This is f sub t. What about differentiate this function with respect to x twice? If you differentiate with respect to x once, you get sigma down. If you differentiate with respect to x twice, you get sigma squared down. So you got 1/2 sigma squared times a function. This whole thing dt. And of course, if you differentiate with respect to x once, you bring sigma down. And so this is f sub x. This is f sub x. And so after all the dust settled, these two guys cancel, giving you with the Black-Scholes model that we discussed. Okay. So, all right. Again, a lot of materials, right? Review this. We'll talk more about this next week. Okay. So I'll answer some more questions. Otherwise, have a good weekend. All right. Yeah, thanks. Okay. So go ahead.
Can I ask a question on problem 4 in the homework?
I can't hear you, Karen.
Can I ask a question on problem 4 in the homework?
Problem 3.
4.
4.
Yes.
Yes.
Yes. So I'm having trouble. I generated the Brownian motion path. I'm having trouble like using it to find.
You're facing in and out.
Oh, I'm sorry. So I generated the Brownian motion across the path, but I'm having trouble using it to find part A and B. I think specifically with like taking the path and finding DWT.
No, you have to generate DWT first and find the path later, right? You understand?
Oh, yes.
So give me one moment, all right? I need to run to the restroom real quick. I'll be back.
Okay.
Okay, so Sinan, do you mind sharing the code that you wrote for question 4? I think you got it almost correctly. So
Yes, I kind of changed it though, but I'll share what I have.
oh no, I'm talking to Sinan because she showed me the code yesterday, and I think her code works.
So you want me to show the code, right?
Yeah, could you?
Yeah. But you are sharing the screen, so
let me stop sharing. So let's take a look at Sinan's code, right? And we'll try to critique that.
This one.
Yeah, can you zoom in a little bit more? Okay, good.
Okay.
So yeah, so right, so DW, right? So let's start with her DW. Okay, so that is correct, right? She generates the differential, right, with n steps, right? Or n n minus 1, whatever, right? And then from there, right, the first one is basically from the DW, she constructs the DS. You see that?
Yes.
Right, that's the differential because the formula says, right, ds is s dt plus S times S mu dt plus S sigma dw, right? And she has to be careful a little bit, right? Where you see this is a loop because she has to start with S0, right? That's what her S1 equals to S0. She starts with a list of initial stock. And as you move time forward, right, you calculate the ds for that time interval, and then you add, right? That's her constructing the SD comment, right? And she add the stock differential to the previous stock price to get the next stock price, and then feed it back to a loop.
Okay, the thing that was confusing me was in like question 4, you say to first generate and store an array of values for the path from 0 to t. So I thought you first had to generate it and
oh,
then like,
you know what? I apologize. Maybe what goes on in my mind wasn't precise. Did I say generate a path of Brown motion?
yeah, you said generate and store as an array of values a path of Brownian motion wt on 0 to t.
Right. Yeah, I guess so. Conceptually, that's what you do, but I guess that's not what you do in code. Because so basically, okay, go down, right? In Shinan's code in part B. That's fine. You can stop there, Shinan.
Okay.
Part B, you see, stock price path. So there you do generate W, right? You see that?
Yes.
Because right, you have to use the value of W in the explicit formula.
Oh yes.
Okay, so you do use it there, and when you construct W, you need dW. So you use dW in the A portion. You understand? But I guess I don't mean, right? Obviously, if you use differential notation, then you don't use the Brown motion path in the differential, right? You use the Brown motion differential, right? But you do use the path in some way because, right, it does enter into, say, step B. Does that make sense? Yeah, what Shinan did here is exactly what I have in mind. Yeah.
Can I ask like a more like theoretical question? Because I was doing something that I know it's wrong, but I'm not really too sure why.
Yeah.
So can I actually see the code for a second? Because it kind of helps. So basically, I generated the whole path W, and then for each dt, since I know W, so like I have, let's say.
You want Shinan to show us to show the code again?
Yes, please.
Shinan, can you show the code again?
Sorry, I saw Karim want to show his code. Sorry.
It's fine. It's fine.
Okay. This one. So, yeah.
Yeah. So we know W, like the W at the, let's say, third index will have a distribution of normal with mean 0 and variance like I times dt in this loop, right? Because
you mean W itself?
Yeah, like the third element in W would have a distribution with a variance of I times dt.
Yeah, you mean the ith element?
Yeah, the ith element.
Sure. Yep.
So what I was doing is to get dw, I was taking that ith element and dividing by the square root of I, and then using that as my dw, but the graph just wasn't coming out.
Okay, so now you want to share your code where the graph doesn't come out?
Yeah, so I kind of changed it because I'm running out of time, but
So I have a vague feeling. Remember in the lecture before where I was showing how you got to be careful when you construct the path of the Brown motion. Otherwise, you might get a white noise. Remember that part of the lecture?
Yes.
Unless if you want to show me the code, I can point to your error maybe, but I have a vague feeling that you are running into that kind of error. Meaning that you, instead of constructing the Brown motion path, you're constructing white noise.
Okay. Yeah, I'll can I send it to you as an email, because I have to like write it up and rewrite what I did.
But so either way, right? Let me point out that even without having to see your code, thinking in that direction is actually not efficient. Because, right, that's exactly how we do not generate Brown motion. Why? Because we cannot generate Brown motion directly without knowing its joint distribution. You understand?
Mm-hmm.
So you're trying to do the impossible in some way, or not impossible. You're trying to do something super hard, right? Because Brown motion, I emphasize again and again, Brown motion is not independent, right? WTI is not independent with WTI minus one.
Mm-hmm.
They have a very specific covariance structure. Now, when you call up NumPy to generate these things, where do you incorporate the covariance structure in it? You understand?
Yeah,
So
yeah.
if you don't do that, then obviously what you're doing is wrong. On the other hand, right, if like what's seen on this here is exactly the classical way for you to get to it. Why? Because DW is IID and NumPy can run IID stuff right away. So from the ground up, right? From the ground up. You run with DW and then you construct a path, you know, directly. Does that make sense? After using DW, right?
Yeah,
So
yeah.
that's the building block. The building block, that's why I spend so much time lecturing on these things. The building block is not the path itself. Yes, we mathematically will approach it like that. But when you code from the ground up. Because otherwise, how do you know the structure of Brown motion so you can ask NumPy to do it for you?
Okay, yeah, I see.
You understand?
Yeah, I understand. Thank you.
Mm-hmm. All right. Shinan, you have your question too, right?
Yeah. Okay. I have a question about problem 2C.
Yeah.
My question is that we have to price one of A, A, and G their option, right? But if we choose 4K, do we need to choose the sigma or just?
No, right. So, oh, by the way, it's called FANG, right? People call it FANG stock.
Okay.
So the point of 2C is it 3 or 2?
Problem 2 part C.
2 is theoretical price. Oh, 2 is the using Yahoo Finance, right?
Yeah, definitely.
So by pricing, right, you understand that pricing is very simple. Why? Because you have the portfolio.
Yeah.
Sorry, you have the replicating portfolio of the
Yes.
Condor, right?
Yes.
So that's what people mean by synthesize, right? Because now basically then the market price of the Iron Condor is just the market price of the individual components in the portfolio add up.
Yes.
That's it, right? So even though the market doesn't have an Iron Condor,
Yeah.
you can construct an Iron Condor yourself by quoting market price of the individual components.
So just do the portfolio of 4 strike price.
So use the market price for the calls and whatever, you know.
That's strike price corresponding price and do the portfolio.
Yep.
Yeah. But at the end, if we return for the part D, we have to plug in to the implied volatility function we wrote by ourselves.
Mm-hmm.
Yeah, they will return just one implied volatility, and I don't know how to compare with Yahoo Finance because Yahoo Finance have a lot of implied volatility with different K.
Sure, well, that's why the question, right? It's a conceptual question. The
So
point is,
that's why I confused for because we were supposed to have for.
so the simple question is, does Yahoo Finance give you a quote for Iron Condor?
No.
So therefore, Yahoo Finance doesn't have.
Yeah, so that's
Okay, I get what you mean. But here's the point, right? You could roughly think of it as what? The Iron Condor combines call options, right? From 4 close strikes, right? Closely spaced strikes, right?
Yes.
So, and that gives you a single number. So you
Yeah.
can think of that single number as a number that represents the volatility corresponding to that range of strikes.
Yes.
Does that make sense?
Yes.
So what that means, right, is that the volatility you found should be close to the volatility of the call option in that range, but it's not none of those numbers because it's a volatility corresponding to a new product.
Okay. So they were in the range of the four
I
strikes.
guess, right, it should be somewhere in that range,
Yeah.
right? But it's not any of those numbers, right? It's like the average of the volatilities of those four numbers in some way.
Yes.
Right.
And okay. And I have also a question for to choose K in the liquid region of the option. What is the liquid region? Is that in the money or?
Liquid means it should be, the liquid doesn't have to be in the money because call option here will be, some of them will be out of the money, right?
Yeah.
Basically, remember that the iron condor ideally is placed so that the stock is in the middle of K2 and K3, right?
Yeah.
So
Yes.
if you choose K2 and K3 and K1 and K4 kind of around stock, the current stock price in a symmetric way, if you can.
Uh-huh.
Liquid, right, has to do with the volume traded, right, and open interest.
Uh-huh.
So you understand what I'm trying to say? So you look at the volume traded, right, and open interest, and if those are relatively high, they're non-zero, then those are liquid, right? Basically, liquid means that they're actively being traded right now.
Okay.
Okay, and if you stay around current stock price, those must be, right, the most liquid region of the option. Does that make sense? So
Yeah.
options are not liquid when their strikes are very extreme, right? Very far away from the current stock price. But if they're close to current stock price, then they're liquid, right? And that's how you should choose your iron condor strikes to begin with.
Yes.
Does that make sense?
Yes. But okay. I think the close of the auction is 4 p.m. right? Because it is now keep changing, and the stock price is Yahoo Finance, the data is keep changing. So I'm
right. So no. So you should just download once, right? You run your
okay.
and you do it for one. Yeah, of course. You're just
Yeah.
exactly the problem of real life application, right? Real
Yeah.
life application, you have to live update your calculation
Yes.
every 5 minutes. So in the homework, you just download once, right? Into the like the notebook, right? Like the applied volatility notebook. You have a snapshot of the range of the strikes,
Uh-huh.
right? You know what I mean?
I know.
And based on that snapshot, then you do calculation down so people would know, right?
Okay. Thank you, Professor.
So liquidity, right, of anything has to do with open interest and volume traded, right? Mostly volume traded. So in Yahoo Finance, right, you have the open interest and volume traded, so you can read. Basically, for call and put, liquid is usually the most liquid is at the money, right? Options. And the illiquid is where your strikes go very far away from the stock price because, right, at those points you don't have trading activities, right? So open up Yahoo Finance. Here, right? So current price for the Apple is 174, right? And you see that if you have strike to be 105, which is very far from 174, right? You have very slow volume. And look at the implied volatility, right? That's absolutely nonsense because this is not liquid, so they're not using any active, price. When you go close to 174, right down here, see the open interest, volume, and open interest, right? Then the numbers, right? Basically around the liquid regions, right? The price, sorry, what's the price? I think around here, right? will be the market price right now. So that's reliable price, right? But if you go far away, right, you see there's no open interest. Basically, your data is less reliable. So you don't want to use the extreme strikes as a quote. Okay. Understand? All right, anything else? Well, so there's strictly nothing, you don't have to be worried about out of the money, right? It just means that the strike is below the current stock price, right? But of course, out of the money doesn't mean it's not liquid. You understand? 174, right? The open interest is very high. So around the at the money region is where it's liquid. Only when you go very extremely out, right? So the keyword is the open interest. And we even open interest, right? For some reason, right here, 167, right? I don't know why it has very low interest here, right? But this is still at the money, I think. I mean, or around that, right? So I don't know why it has very low open interest, but or low volume, sorry. Oh no, it's not low volume, right? Yeah, it's low volume. I don't know why, but you know, it's fine, right? As long as you stay around this region, you're fine. So yeah, someone else saying something.
I have a question about problem 1, part C with the Monte Carlo simulation.
Yeah.
I went to Cesar's office hour yesterday, but still can't figure it out. So we're supposed to compare this with our answer in B, and you're saying it's supposed to be very close. But I don't know how we can make sure that, you know, they're gonna be close. The answer I got is like pretty different.
That means you're wrong.
Yeah, I figured. So
One second. So yeah, Eugene, right? Yes, that's the rule of thumb. But again, right, as with any rule of thumb, just look, right? Again, like I said, right? Look at volume and open interest, right? Liquid means actively traded. Illiquid means not actively traded, right? Or no availability. I mean, if the volume traded is like this, right? Anyone would say it's illiquid, right? That's all I'm saying. Now, the fact that this corresponds to extreme strikes is an observation that seems to make sense to me too, right? But definition is low trading activities or no trading activities. Does that make sense? So using that concept, right? Use your judgment to see what you want to choose as illiquid, right? No one can tell you this is this and this is this, right? But based on your understanding, right? Then you can pick the ones that make sense. All right. Cyrus, do you want to share your code? We'll take a look.
Okay. Can you see my screen now?
Yeah, I see it.
Right, so this is my part B.
Yeah.
I first used the generated Brownian motion.
Yeah.
Use the explicit
By the way,
formula.
right, for that one, you are doing the inefficient method.
Right.
Because you're doing the European one. So for pricing, you don't need to generate the whole path. You only need to generate one single normal, right?
Uh-huh.
You understand?
Yeah. You mentioned
But that's
earlier.
fine. It's not wrong. It's just that you run the whole path and you only use the last value, so you don't need it.
Yeah, that's true.
Okay. So
yeah. So this is how I be able to get the payoff for our Condor. But when it goes to Monte Carlo simulation, so what I did here, I think my understanding of the simulation is basically take the average of all the payoff for the iron Condor
Yep.
So I do like a double loop thing, and I take the average in the end. So I generated like a list of payoff values and take the average.
Yeah, that looks fine. Go down.
But this is the VT that I got in the end.
Uh-huh. Go up.
So I think because I'm generating like different Brownian motions within the loop,
No,
I don't.
hold on. Actually, that's your. Oh no, it's. Wait, hold on. It's weird here. You have two I, right, in your loop.
Uh-huh.
That I will be confusing, right? Would it?
Oh.
Okay, you exhaust that I, that's fine. But I would call it J, right, for the second one.
Mm-hmm.
You know.
Right.
So it's fine. And then you should change that to J, right, down the road.
Yeah.
So you generate, and then you store that in the Monte Carlo. And how many? What's your N?
My N is like 1,000.
Oh no, 1,000 is not good enough to cut it for Monte Carlo. So
Oh.
run the code, put hard code N in there, N equals to, let's say N equals to 10,000. Yeah, run it again. Or you have to import NumPy. Yeah. Okay, go down. Yeah, run the code again.
It's still loading.
Okay. But you probably have to run it from the beginning. Yeah, you see, this is why you have to code your code efficiently. So running the Brownian motion path is also hurting your computing, right? Because you don't.
Yeah.
So it's fine.
But when we look at part B, like when every time I run, I get different payoff for the iron Condor.
Hold on. Yeah, of course, because it's random. But part B, I asked you to do the Black-Scholes price, right? I'm not asking you to do the payoff, am I?
You're asking for the price of the iron Condor.
Right. I didn't ask for the payoff.
Right.
So are you showing me part B here? That's
Yeah, this is part B. Then I think
where's the price?
I think I'm confused about like how to calculate the price. I kind of code it as if I payoff equals price.
No, payoff is payoff and price. Payoff is the future value. Price is the current value.
Uh-huh.
Right? So price here is equal to the price of the Black-Scholes adding up.
Price of Black-Scholes adding up.
Yeah, I asked you to find the replicating portfolio, right?
Uh-huh.
Did you find it? Right. So well, put whatever. So there. What that means is the price of iron Condor is price of Black-Scholes put K1 minus price of Black-Scholes put K2 minus price of call Black-Scholes K3 plus price of Black-Scholes call K4.
Okay.
Understand?
Yeah, I see.
So your part B is actually wrong. You're not even output anything sensible for part B.
Mm-hmm.
Right?
Yeah.
So you have to fix your part B, and assuming your part B is fixed, then your part C with a high value of Monte Carlo should match part B.
Okay.
Payoff is not price. Understand?
Yeah, I would try it out. Like originally I did part B, the V I was doing payoff. So I guess that's not right.
No, it's price.
Okay.
10, right?
Yeah. All right. Thank you. I will test it out more.
Okay. All right. We're all good. Cool. Awesome. We're good. We're good.